Hey, gang.
Hey,
Good to see
Swahi.
everybody. So, Willie, tell me about what happened last week with the pilot's license stuff.
I passed, so I'm officially a pilot now.
Nice. That's awesome.
Yes, sir.
Congratulations.
Thank you, thank you.
Constant presence.
Do you do the math homework?
One of them.
Do you understand that?
Could I check to see that I'm sharing through Adobe Connect like I hope to be?
Yes.
Yes.
All right, great. Thanks, guys.
Hey, Mr. Walker, this is Margaret, and I just wanted to tell you that my power is out in my house, so I'm actually at a library right now, and so I just want to make sure if you can hear me because I'm whispering a little bit. Okay, cool.
Yeah,
Thanks.
yeah, hear you really well. Is that part of a storm or something else?
I have no idea. It's like 60 degrees out, and then it's supposed to drop down to 40 tomorrow, so there's some kind of weird weather going on. It's not snowing because I'm in North Carolina. I don't know what's going on.
Yeah. So, Margaret, is it power beyond your house, like neighborhood out kind of thing, or?
Yeah, there's a tree down somewhere,
Oh,
so I had to drive into town and
okay,
hang out at the
yeah.
library.
Glad you were able to make that work. Thank you. Yep. We'll understand if you switch to sign language at some point. And you can text in too, and I'll explain to the class what's going on with you if that's okay, just so that they know. Thank you for that.
Yeah, I should be able to talk. I was able to do this for my last class, so I think it'll be all right.
All right, cool. $36. Hey, Max, what's up, buddy? How you doing, man? Thank you.
There you go. All right.
All right. Happy day.
All right. Thanks.
Hey, Maurice. Hey, Chandler. Hey, Maya.
Checking back in real quick. Did
Oh, yeah, I'm glad you checked. I don't know either. But, let me just mute for a second. Thank you. Thanks for checking. Maya, you coming in from home again?
Yeah.
You got a lot of snow up there?
I don't know what we're at right now, but it's supposed to start snowing again, and then we're gonna be at like 1.5 feet.
Whoa. Man. Yep. Hey, Robin, welcome to class.
Whatever the weather was yesterday was weird.
Weather yesterday?
It was just like wet snow
Yeah.
into like a little bit of hail and sleet. It was just
All right, let me do a roll call because I'd love to get started if I can, but it doesn't look like I have everybody. I've got 4 from Fort Worth Country Day. I've got Margaret. I've got Maya. I've got Robin. I've got Max. That's 8. All right.
Chandler and Maurice were here.
So who?
Chandler and Maurice were
Yeah, Chandler and Maurice are here. That'd be 10.
there.
Then I feel like Olivia emailed me saying she couldn't make it today. That would leave Sumvit in Florida to need to come in. So let's see, Olivia. I'm pretty sure Olivia's got to be absent today. That leaves Sumvit, and then hopefully those other two guys, Chandler and Maurice, will come back in. Let me just talk to people a little bit while I've got you just before we get going for good. Maybe I'll start with Fort Worth Country Day. Are you guys all set for a test option, either taking it tomorrow or Wednesday?
Yes, I think we're good.
All right. Hey, Maurice. Hey, Chandler. And then, hey, Sumvith.
Hello.
Welcome to class. Dallas Fort. All right. So I'll be sending that to your administrator there at some point tonight, so they'll have it. Margaret, you've worked this out with Ms. Obey. Chandler and Maurice, are you guys set for taking a test either tomorrow or Wednesday at your school somehow?
We're taking it on Wednesday.
Wednesday. All right. Maya, did you have school today?
I didn't have school today. I don't know if we're gonna have school tomorrow because even if the snow clears up, it's supposed to rain and it's supposed to be -17.
Wow. So Maya, one option might be to take it at home with a parent or guardian proctoring. If you're snowed out, for example, did you plan to take it tomorrow or Thursday or Wednesday? Did you have a best?
I never talked to my teacher, but in my head it was Wednesday.
Wednesday. So maybe you and I should stay in contact, and if you're snowed out, do you think maybe doing it at home would work?
I think I can do that.
Okay. And Robin, I think I'll email you. I think we got it set up the way we did last semester with you, okay? So making a note. And then, oh, wow.
It says you stop sharing.
I hit a button.
Sumvith, quit hitting buttons.
I hit a button. Stop presentation. There.
Sumvith, you're a bad kid. Wonder what that caused to happen. So you stopped my. Let me see if I can go back into Adobe Connect then. Or I wonder if I have to do that through Blue Jeans. Let me see. Sumvith, that's really funny. I'm gonna try to go back in. That's not letting that happen. All right, so there's my presentation, but no one can see it anymore. Presentation gone, so let me see. Does that mean I go back through Blue Jeans for this? That's not it. Blue Jeans. All right, guys, here's what's going to happen. I think I've got to leave the meeting and come back in, I think, to make this work. So you'll not see me for a little while, and then...
Chad Evans.
Yes.
Hello.
Hello.
Random question of the day. Here's the random question of the day. Do you have a stuffed animal?
Probably. I think I have a few.
You have a few. Perfect. See the Google Doc for more details.
I've read. Yeah, I've read the document.
Mate.
I think we're good. I think we're good with that, some of it.
All right, mate.
Hey, which one of you guys is Joel?
That's me.
Wait, so Chad, you're the one at far left?
Hi, Joel. Did
I'm
you
this
work on
one.
Hello.
I didn't work too much on it. I'm gonna start it tonight. I got in kind of late.
No, it's not a problem. Yeah, I got in kind of late myself. I only made a couple questions, so.
Yeah, I did one question, and we can start working out the answers too.
Oh yeah, we're back until somebody cuts us off again. Now, does that bring back my presentation or not? You know what? Let me switch my layout and see if that makes a difference. Constant presence. I still have constant presence. So wonder what happened to my... So you guys still can't see my presentation though, can you?
We should try the unplug plugin.
Oh yeah, let's try that. Maybe that's the deal. Thanks, Max. I got Max here as a technical advisor to help me with anything I can't do. Does that bring? Yeah, here we go. That's what we should have tried the first time when Sumvith messed with us. Are we back? Can you guys see the presentation?
Si, senor.
Sumvith, what button did you find, man? It's like the master shutdown. Don't find it again.
On the life-size remote in my conferencing thing, I just hit the start presentation button. So basically, it's good for So
all
I
right,
can
don't
just
hit it,
and then hit the same button to stop the presentation.
All right, cool. All right, I think I figured out how to solve that problem if it happens again. Appreciate that. Sumvith, you all set to take a test for us either tomorrow or Wednesday?
And Wednesday? I can do Tuesday.
Tomorrow or Wednesday?
Tomorrow I think I'll be doing it. My curriculum director wants me to take it. That's what he prefers, so I'll go with that.
Okay. All right. Sounds good. All right, gang. I think we're back now. And Max is feeling Wednesday. Thanks for adding that in. So I just want to make a mention. Are you guys talking to each other as a group? I haven't had many people share a Google Doc with me or include me in on it. Maybe they forgot to do that in terms of trying to work on a presentation for their dating game. I'm pretty sure one group has shared the Google Doc with me, but remind other groups to include me in on that.
I sent the link to you, Mr. Walker. Did you get it from me?
Yeah, I got it
cool.
from you, Margaret. Yeah. Oh, Margaret wanted me to let you guys know, or this may be handy for today. Margaret's not at home because power's out in her home, so she went to a local library. So if she seems like she's talking a little more softly, that's what's going on. And we don't want to get her in trouble there. And if she texts in anything that we need to say, just let me know, because I tend to not watch the text chat going on in class very much, just because there's so much else going on. Let's see. I'm eager to kind of jump into our finish up our discussion and make sure we feel really good about the nuclear power plant and how that works. And in terms of questions that are reasonable for our test, I think pretty much anything we've been doing in our shared Google Doc on nuclear would be fair game. So, like how to balance a nuclear reaction, where I give you certain things, like I say, this isotope is an alpha particle emitter, or this isotope is a beta particle emitter. I'm not expecting you to necessarily know that something would be an alpha or beta particle emitter. That's a level beyond us, though we can talk about some ways you might figure that out. And, honestly, I want to just tell you in advance so that there's no secret. There's going to be an essay question, and it's just going to be, how does a nuclear power plant work? So you're going to want to go into every kind of detail you can, like, explain, and there'll be some leading questions, but you're going to want to, explain the whole deal with the fuel, like what is the fuel, and, what is enrichment, and how's the whole nuclear power plant work? So we're going to want to make sure we understand how control rods work, the moderator, coolant, how do we generate electricity, the purpose, all that kind of stuff. And we can review some of that and make sure we're clear on it today. But I don't want that to be a surprise. That's kind of like, hopefully is to be expected almost. If you'd like to use a word processor because you think that would be faster, that's fine. You can also write by hand. But I've told your administrators at your schools that if you'd like to word process, that's fine. I just ask that you only use a word processor and don't have any other material there, no internet, no phone, that kind of thing. Any questions before we jump in? Casey.
Okay. How much time are we going to have to take the test again?
Great question. Most class periods at most schools are usually 45 minutes. Some might be 50. So I told your administrators I'd try to have it, be like a 35 to 40 minute kind of deal. And I'm not a stickler on time. So if you need more time than that and can work it out at your school, it's okay. I'll try to make it on the shorter end because I realize it's hard to judge. Any other questions? Okay, well, let's jump back into our shared Google Doc. Can we find that? I got to pull mine up too. It's nuclear. I have so many Google Docs named nuclear, it may take me a minute to find which one it is. Not the PowerPoint. Nuclear Notes, there you go. So Nuclear Notes 15 is the title of this one.
If we just
you guys probably have a few.
Be good to go, you think?
Max is asking if we just know this stuff, we should be good to go. You know, I think so. I tried to make it so that we were keeping everything in pretty good, context as we were going through. Yeah, I think we should be good. And just so I'm clear, I'm not going to ask any specific questions from Disappearing Spoon. That's not my, it's not my deal to expect you to have memorized, this character in history or this this chemical compound or whatever like that. So it's really our first test is on nuclear topics. So I'm hoping that just by being clear there, we'll be okay. Where are we on this then?
21.
Where? 21. So it says, why does an electric power plant need to be near a body of water? Before we go into that, I want to backtrack to see how we're looking on 20. Let's look back over what we were saying on 20. This would have been last Thursday. What happens to the heat generated by the fission reaction? Water is converted into steam. It's directed into a fan, which spins, and the fancy word for that is a turbine. That generates electricity via a spinning magnet. So the spinning fan spins the magnet, which is a form of a generator, past a wire. That generates your electricity, and then you're good to go. Can we maybe just take a little bit of a look? While we're still on 20, but I want to take a look at a nuclear power plant and look at the diagram itself. So look at the Adobe presentation, and let me go to, I think I want to go to slide 36. So let me find that real quickly. Yeah, can you guys see that reasonably well? Okay. So this shows the outer containment shell is the first thing that you see there, which, if you watch the video, it was a fairly short video in the reading before class that was from the URL. They showed that it's a big, at least in the U.S., it's made of multi-layer of steel and concrete. The idea being that you don't want a plane to be able to go through it, or you don't want an earthquake to be able to bust it up, or you don't want any other kind of natural disaster to cause it to be a problem. If there's a problem inside the power plant, it should be that containment shell will hold it in place. It's really built to withstand a lot. So that's a safety feature. And they vary a little bit around the world. And if we end up talking about what happened in Russia at Chernobyl, we'll talk about they really didn't have a containment shell. It was almost like a warehouse top that they were not expecting it to blow up, and it just blew the roof off. So, and I think at some point I'd love for us to have a little conversation about what happened at Fukushima, the Japanese nuclear disaster, when the tsunami hit there. Because, again, that was something that they didn't expect and obviously caused a problem and continues to cause a problem today. But anyway, getting back to this, so we've got if you look inside let's see, what are we calling that? The reactor itself, there's the fuel elements or fuel rods. Control rods can go down in between them, as we mentioned, or it can be pulled out in varying levels and degree. But here you can see the water being pumped in. I would consider the water here a coolant, but it could have a second function. Can anyone tell me what the secondary function of the water could be?
We're talking about this.
Sorry, yeah. Let me pull out. Thanks, Max, for making it clear that I'm not being clear where I'm talking about. So if I'm pointing to this water here, this water is pumped in past the fuel rods, and it absorbs heat, and then it comes over here, and it transfers its heat to another bit of water, which is cycling in a different cycle. So maybe I should follow the whole process through. This water gets heated, comes over here, and releases its heat into another, passing through this container here. This is probably a metallic, good conducting metal that passes it into here, and then it's cooler as it returns, and then gets heated up to super high temperatures again, releases its heat, cools, and then warms back up in this cycle right here. So this water never comes in contact with anything else other than this closed loop. And then I'll then pick up and realize that there's a second bit of water that this water here, this may be a darker blue water, this water absorbs heat sort of indirectly from the reactor, and it actually is under a lower pressure, so it boils and turns into steam. And this expansion here is the water molecules are very close together, and they move into steam molecules, which are very far apart. That creates a pressure, and that pushes and makes this fan turn, which is the turbine. So it spins the steam turbine. And then this spinning turbine then spins a magnet, and that's where your electricity is generated, and they show electricity coming out here. Now on the other side, so again, we're going to be looking at this loop here. So it's a secondary loop. The water that turns to steam is still water. It's just gaseous water that we call steam. So then that steam is then condensed itself by a third loop of cooling water coming through. So this water is coming by actually in this direction like this. So this is coming from a large body of water out here being pumped in, and it comes up, and then again through good metal conducting pipe, it absorbs the heat from the steam and actually condenses the steam back down into liquid water, which then comes through, gets the heat from the nuclear power plant water, converts into steam, and that expansion occurs, spins the turbine. It's cooled by water coming from another source, back to liquid water again, comes over here, absorbs the heat from the nuclear power plant, turns to steam, and again, so we constantly are making this fan turn as it goes by. There's positive pressure over here as the water goes from liquid to gas, and there's what I'd call negative pressure here. There's no such thing, so I have to be careful with my wording here. But it's almost like we create a partial vacuum. That's a better word than negative pressure. Because the steam, where the particles are very far apart, condenses back to liquid water because of this cooling. All of a sudden we have a low pressure here and a high pressure here, and again that helps create this wind that's going through, if you will, that's turning the turbine. So again, it gets a little complicated because you've got, let me grab the right thing, you've got this internal loop, and then you've got a secondary loop of water, and then you've got possibly a third loop of water coming in here like this. Now, this probably is not better thought of as a loop as much as just a cool source coming in and then a heat sink going out. You would never really want this water coming back, so hopefully this is upstream where I'm pointing, and this is downstream, water flowing by. You bring in your cool water, and then you release your warmer water. All right, so let me stop for a second, and if we have questions, maybe we can refer to this as loop 1 water, or loop 2 water, or our cool body of water passing by. Max, you have a question?
So
and then some Vith.
This is the pressurizer method or whatever for the.
Yeah, so you've probably been reading. There's pressurized water reactor.
One loop, or what's the?
And then there's a boiling water reactor. So in a boiling water reactor, the heat would actually, in this very first loop, cause the water to turn into steam. Not here, that would be dangerous, but somehow off to the side it would turn into steam. So almost imagine that somehow this connects right to here, and it would turn into steam, which would go directly to your turbine. I don't know as much about that kind of reactor, but I feel like it might be a little more efficient because there's less needing to convert, but I feel like it's a little more dangerous.
Yeah, that was my second question, because it said in the video that the
pressurized,
uses way less uranium, I'm pretty sure.
Okay.
I don't know if you knew the answer.
Yeah.
Because I figured it would be the opposite, because it seems like there's much longer process in this one.
Yeah, this is going to push my knowledge, and not sure exactly why. It's a good question that I don't know the answer to. But thanks for bringing up the pressurized. This stays under such high pressure in this first loop that I'm flipping through that we never ever see it turn into steam. It just transfers its heat over to water that is at a lower pressure and can turn to steam. Samvith, you had your hand up. Is your question still there?
Yeah, it was just going back to this whole efficiency thing. It was just like you have the uranium fissioning in the fuel elements, but the fact that there's so much water involved in this entire loop just makes me wonder how much of that energy actually makes it to becoming electricity, and how much of it is just wasted.
Yeah, it's a great question. I think this process in general is on the inefficient side, and if you don't mind, I think it's such a good question, the efficiency question, that I really can't answer very well, but I'm going to backtrack just a little bit to make it clear that look at this reaction, and this is the exact same thing. The difference is down at the bottom it says chemical energy turned to heat. So this is what we also do a lot of in this country and in this world is we burn things like coal, like natural gas, and like petroleum. And one of the things we can do with that heat from chemical reactions is we can again use that heat to heat water. The water turns to steam. That expansion creates a pressure, and this is probably a little better view of seeing these turbines where you can kind of imagine them going by and making these fans spin. So I kind of like this picture a little better. Then that spinning thing, the spinning fans or turbine is on a rod that then gives you your kinetic rotational energy. This is what turns your magnets past wires and generates your electricity, and then your electricity flows off. So the question, in a sense, is this is a fairly inefficient process, and it really doesn't matter from the efficiency question that Samvith is asking, which is an excellent one, whether you're heating with nuclear fuel or whether you're heating with chemical energy. There's a good bit of inefficiency into this. So I love the question. But in terms of large-scale generation of electricity, and just while we're there, this just shows in this country refers us back to if we burn coal, again, the way we get the electricity is just like in a nuclear power plant. If we burn natural gas, it's just like this. So what we're learning in terms of generating electricity is the same for coal, for natural gas, or nuclear. In terms of it generating electricity, it would be the same for petroleum. It's different for hydroelectric because falling water turns the turbines. So there's no burning or no heating involved. And then other renewables would be things like wind power, which turns the turbine, or solar, which actually is a way of generating electricity directly through the sun's energy. So Samvith, I like your question. It's a very good one. I'm going to go back to our nuclear power plant. Our difference here is that we're generating this by nuclear means, not chemical means. Excellent question. Thank you. Others from the class before we go on. Casey.
This is just kind of like a logistics question, but wouldn't the heating of the water that's used as a coolant and like that's pumped into the larger water source, wouldn't that contribute to like raising ocean temperatures and global warming potentially? I don't know.
Okay, thank you, Casey. Good question. So I think we're referring to the water over in what I'd call loop 3, if we will, and it's not technically a loop. So you are pointing out something that in this case, the water comes in at 27 degrees Celsius and is going out at 38 degrees Celsius. I think those are just reference numbers by example. It might depend on lots of things like how fast the water's moving through, etc. But you're bringing up a good point. And one way to answer the question is yes. And another way to answer it is remember, as long as we're generating electricity, it's going to be the same amount of heat put into the environment, whether we're burning coal, whether we're burning natural gas, or whether we're using nuclear. And again, I'm not trying to be pro or con. I'm trying to make sure we're very clear here. We demand electricity. That's sort of a fact. And we can work on trying to demand less. Like we can cut the lights out when we're not using them. We can conserve energy. We can do all kinds of things. We can be more efficient in terms of the way we insulate our homes. But at some point, we demand electricity. And at some point, we've got to ask ourselves, yeah, what are the costs? And so one of the things we do is that we are warming the water up here. It's more an issue for, this can be an issue for fish and aquatic life that's used to a certain temperature of water. This is a process called thermal pollution. I don't know if you guys have ever heard of it, but when you warm the water up like that, it's called thermal pollution, literally heat pollution. And it can be a problem for aquatic life in the close environment. Manatees love this stuff, though. I'll mention this because, Somvith is in Florida. Manatees actually love coming up into the water of a any kind of power plant where it's warmer. They like warmer water. Again, you may be throwing them off from other cycles and things like that. All right, we divert. Any other questions? I can't tell if it's Joel or Chad.
It's Joel.
All right,
kind of on what Casey was saying. There's a lake nearby that has a nuclear power plant, and it's really good catfishing in the winter because normally the catfish are kind of dormant during the winter months and stay really deep. But because it's constantly warmed, it's kept at a constant temperature. So the fishing is actually better in the winter.
Huh.
And so, it just kind of does affect.
Yeah, good example. Let's see. So again, in terms of what you guys, if you were trying to describe this to someone or say you were trying to answer a question on a test and try to make this not too complicated, let's talk about the purpose of the water. I would say the water in this reactor has a 2 to possibly 3 purposes. Can someone maybe just tell me what one purpose of the water flowing by is? Willie.
Acts as a moderator.
Excellent, good. Don't forget that this water is acting as a moderator, and we can go back and review that. Maurice, what's another thing?
I actually had a question about.
Go ahead.
I guess another thing would be kind of the removal of excess heat to recondense the water. But I guess I had a question about the moderator. Like when it slows down the neutron, does the hydrogen and oxygen kind of break apart? Do the water molecules break apart? Or?
No, my understanding is no, that it just the passing by and somehow interacting as it goes by is what's slowing the neutron. But my sense is that we're not splitting water by that process. That's somehow just the passage through it is slowing it down. Now, in terms of exactly the physics, if you will, going on there, or if there's chemistry, I'm not aware of anything beyond that. And again, my specialty is not nuclear chemistry. It's just sort of something I, have an interest in, but not to that kind of level. So I can't answer it much beyond that. So I don't know.
All right, thanks.
And you answered the other part. So the water has a dual purpose. Willie said it's a moderator, and you added it's also a heat sink. So you need the water to pull the heat away from the reactor. And remember, your goal here is to generate electricity. So it's an integral part of that, in that it's drawing heat away, which then heats water in a secondary loop that turns to steam. That expansion turns a turbine. That spinning turbine turns a generator. Generator generates electricity, and you've met your goal. Any other questions about these loops here? Do people feel like they could explain the purpose of the water in a nuclear power plant? Okay, good. Feel like that's pretty much it for the insides of the nuclear power plant. So let's go back to something. How long do the fuel rods last? I'm gonna ask you a couple of review questions that we've been over before. Anybody? Maya?
3 years.
Yeah. And we replace a third of them every year. So they last for 3 years in a nuclear power plant. If this were a coal-fired power plant, we'd have to be pulling the train up, unloading the train, burning it. It produces carbon dioxide, which goes up into the environment. It's a greenhouse gas. It contributes to acid rain. The coal has things like mercury in it, and you end up putting that up into the environment. That rains back down into the oceans, gets into fish. So there's all kinds of problems almost with any of this. I want to talk about some of the problems with nuclear as well. Maurice has his hand up, though. Go ahead.
Oh, yeah, I just kind of, in the reading, some of the reading you assigned, I don't know, I stumbled across something that said that 1/3 of the power actually comes from like transmuted U-238.
So what's that? Yeah. So what happens there is some of the uranium-238 actually can turn into fissionable isotopes that can then themselves, accept neutrons, undergo fission. So yeah, if you guys want to study nuclear even more and take it to the next level, I'm sure you could take a college level course and then a grad school level course and ultimately become a nuclear engineer. One of the reasons you have to be careful with nuclear waste is it can generate other fissionable products, and the military, has interest in this. So they actually do some nuclear reactors just for the point of generating fissionable material. So plutonium, for example, can be put into a bomb. It can be chemically isolated and then used. And there are certainly other types of reactors. But it brings up all kinds of issues in terms of our world and who has nuclear power and who doesn't. And then if you have a nuclear reactor and you're only doing it for peaceful generation of electricity, or are you also somehow siphoning off fissionable material that could then potentially be used for a bomb? So, that's some of the political stuff that gets to be an issue within our world. So great, Maurice, great question and comment on that. Thank you. Anybody else on anything? Where were we? We were talking about, okay. So the fuel rods last for 3 years. But what happens after the 3 years are up? Has anyone found anything about how we're dealing with these things when we're done with them? Anybody find anything about nuclear waste or the whole plan? Casey, help us out a little bit.
I know they store a lot of nuclear waste up in Chernobyl, where the Russian nuclear plant exploded. So you're there.
So let's pull back to the U.S. Do you know what happens to nuclear waste in the U.S.? And then I want to stray a little bit away from Chernobyl, but anybody know anything about nuclear waste in the U.S. from any of the reading? Maurice, and then we can go to Maya.
Right now they just kind of mostly do dry cask storage, but they had this Yucca Mountain idea, but they kind of scratched that. So right now it's just kind of building up.
Yeah. Can you know where Yucca Mountain is and what state?
Montana, right?
I forget, but I believe that's probably right. It's one of the fairly remote western states, Montana. The idea at Yucca Mountain would be to go deep underground and bury nuclear waste there. Robin, do you have something to add to that?
I was just going to actually mention what is actually happening here in Europe. Basically, there's a place in Germany where it's sort of stored under a mountain which actually has salt deposits. And basically, it's not really an accident, but what happened was that actually water leaked inside. So that was sort of an issue that arose there in Germany. But yeah.
Okay, great. Thank you for that. Because different places are going to deal with it in different ways. Samvit.
I think it should be worth noting, just a geographic thing. Chernobyl happened in Ukraine, not Russia.
Thank you. Yeah, I appreciate you pointing that out. Thank you for pointing that out, and that's definitely my mistake for saying that. I thought when that happened that was all part of the Russian state, but you're right on correcting me there. Thank you for that. Let's see. So getting back to the U.S., we've got roughly how many reactors in the U.S. again? What's our number?
100.
About 100. Here's one of the problems. Nuclear power started in about the we've had it going on since about the late into the 70s, late 50s, 60s. Congress has not yet decided where nuclear waste is going to go. So that is part of an issue, too. It's a big political thing. They keep wondering what's best, what's best, what's best. And right now, you need to realize that every nuclear power plant is essentially storing their waste on site. So right now, there's no agreed upon place in the U.S. to take it. This is at least commercial nuclear power plants. Now, if you find something online that, you can correct me, there may be some movement within a state, but as far as I know, there's not much, cross-state, interstate movement of nuclear waste to one repository, and there's certainly no agreed upon place for that. So that's that. I mean, we got to be clear. That's a problem for nuclear power. So if you're thinking about the pros and cons, sometimes, somehow, the waste has got to be handled and dealt with. And right now, the best maybe proposal is deep underground burial, but where? Margaret, go ahead.
I wanted to point out that for that underground burial to happen, you have to transport very hazardous materials. So, you see when you're out on the highway even that giant trucks are, getting crashed all the time. But, it's because they're carrying fruit or whatever. But if you're carrying, dangerous material like that poses a significant threat too.
Yeah, Max. Good point, Max.
I'm taking a step back. What is it that makes the waste so hazardous? Is it just the radiation?
Thank you. Yeah. So I realized just as we were getting into this, we needed to go back a step. What is it that makes the waste so bad? The problem is the waste itself is radioactive. So when you go back and think about those fissionable products, those themselves are unstable and they radioactively decay. So let's talk about a couple things. One, as soon as let's say a fuel rod is no good anymore, it's had its 3-year lifespan, the first thing that happens is it's pulled out of the reactor and it's actually taken and put in a pool of water. Now that may seem weird. Let me flip to a couple slides. I think I have a picture of some technicians. It's actually dropped down to the bottom of a pool of water, and the reason for that is it's actually thermally hot for a certain period of time. I believe it's a number of years, and I can't keep the number in my head, but it has to be stored underwater for a certain amount of time. Basically, it's generating heat still, but this time it's heat it's not quite efficient enough to be used in the nuclear power plant. It's just kind of as it's continuing to decay. At some point, it gets cool enough so that it doesn't have to be stored underwater, and then at that point, it's a solid waste that just has to be isolated and kept away from anything that's living because it's, again, radioactive. Some of the half-lives can be up to thousands of years, and so here's something where, again, we've got to think long term in terms of burial. Some would argue, and I want you to make sure you realize this, what you've dug up out of the earth, the original uranium was radioactive, and so maybe an argument might be, well, what you end up is also radioactive, and you just have to protect yourself from it. I believe the degree of radiation after the process is higher than it was before from the natural uranium. And again, figuring out a way to isolate it for a long time is an issue that proponents of nuclear power have to deal with. If you're living in a country that's generating nuclear power, which is all of us are, I think, as responsible citizens, we got to figure out a way to deal with it. And, you guys are the future scientists of the world, possibly. So maybe that'd be something you'd be interested in helping to figure out in the study. So waste is radioactive. It's thermally hot for a number of years. And then it just has to be isolated and kept away from people. Do we have anything in our nuclear notes that help with this if we get back to number 23, what waste products are produced by our nuclear power plant? Someone has written in nuclear waste is stored at the nuclear power plant usually. Thank you for doing that. Could we get someone to add something to the effect of the It's radioactive byproducts. They're thermally hot for a number of years, and then they're radioactive for up to thousands of years. And again, it's various radioactive particles. So some might have half-lives of just a few years, and others have very long half-lives. Can anybody address number 21? Why does an electrical power plant need to be near a body of water? Max, what do we want to say there?
For the cooling purposes.
Yeah, basically used as a coolant, for cooling purposes. What if someone were talking to you at the dinner table and they were like, I don't like the fact that you're catching fish down at the, the local pond or lake that, the catfish that is getting that water from that nuclear power plant, aren't those catfish radioactive? What might you say to someone that had that concern? Anybody? Willie, help us out.
I'd tell them that, like, the fish never came in contact with radioactive water. It was just, like, they came in contact with heat.
Good. Yeah, totally true there. Any of the radiation is definitely inside that power plant and shouldn't be getting, it's only the heat that's escaping into the next thing. Everything should be contained within inside. And I'm going to help you guys out with 22 a little bit, which says compare the energy released from a gram of uranium undergoing fission to a gram of methane. I've got a slide that I think will help. Let me backtrack just a little bit. This slide right here. I wanted to compare nuclear changes to chemical changes, and I think we've talked about a number of these already, like nuclear changes involve changes to the nucleus, but chemical changes involve changes to electrons. You can either share or lose. In a nuclear reaction, atomic number and mass number are conserved, whereas in a chemical reaction, atoms are conserved, meaning you don't lose atoms. In a nuclear reaction, one element can actually change into another, whereas chemically that isn't true. Just to help us, though, in terms of the enormous energy differences, let's look at the chemical side first. If you chemically burn a gram of methane, you get 56 kilojoules of energy out of it, heat energy out of it. If you nuclearly react 1 gram of uranium-235, you get 8.2 times 10 to the 7th kilojoules. Can we just do a little bit of rough, let's say that's 82 to the what power? What would it be if we changed it to 82?
A million times more.
To the 6th.
Good. It'd be 82 to the 6th, and then the 6th is, so basically it's a million times more energy if we say 82 is roughly the same as 56. So I think that's a pretty powerful point to make if we go back to our nuclear notes, that you can pretty much expect to get about a million times more energy per gram out of something when you undergo a nuclear reaction like fission, when you compare it to the chemical process of combustion. And maybe I could get someone to sneak that in there just as a rough thing. Now, it doesn't mean that every single time it's going to be exactly a million, and there are other compounds other than methane burning, but just as an example. And part of what's happening is much more energy because energy and matter are interconvertible, so you're actually destroying a little bit of matter in the fission reaction and helping to generate so much energy. Samvith, is that hand up? Go ahead.
Is it safe to say that one can do energy per gram and like gram for gram, because uranium and methane has significantly different molar masses, so I don't know if that contributes anything to this one discussion.
Hey, that's a great point. Yeah, it's a wonderful point. So obviously uranium can undergo chemistry and chemical reactions. So yeah, even if we account for that, uranium's like 200 and something grams per mole, whereas methane's 16. That would be maybe a factor of 100 or 200. Yeah, it's really because we're changing the nucleus, and it really is that big a difference between a nuclear change and a chemical one. So yeah, thanks for wondering about that. But I think we can actually say the enormous, power of a nuclear reaction is, again, I hate to go back to the bomb, but chemical bombs have killed lots of people and more people than nuclear bombs. But one of the, one-upmanship in terms of warfare is ultimately to go, the biggest chemical bomb you can come up with, and then ultimately a nuclear bomb pretty much overwhelms that because of the enormous energy changes involved here. Just as a slight aside, you guys hopefully realize that you guys rely on nuclear power in a very, very different way, and it's a very natural way from the sun, which is a nuclear fusion reaction. Most things in terms of energy on Earth is ultimately solar powered. Even wind power, you could argue hydroelectric is solar powered. If you really want to push it, ultimately the energy in anything like coal, natural gas, and petroleum came from the sun millions of years ago. So we're using that old energy and burning it up slowly. All right, let's keep going. Okay, who can help me with 24? What waste products are not produced by a nuclear power plant? What you want to do there is compare it to, say, a coal-fired power plant or something else. So, Robin.
One product that isn't produced is CO2.
All right, carbon dioxide, that's a good one. Anybody else? Willie, you had your hand up. Was that for CO2?
Yeah, well, I was just going to say, like, greenhouse gases in general. Like, a nuclear power plant only really, the byproduct is pretty much only water.
Yeah.
Like steam.
Good. True. Robin?
Also, I think we mentioned mercury previously can also be released from a coal power plant.
Yeah, so coal, for example, is going to release mercury and other things. I'd want to throw in acid rain gases because the burning of CO2 releases those as well. I'm sorry, the burning of coal and natural gas and all that produces acid rain gases, especially coal. Coal can have some nasty stuff in it. It has sulfur compounds or sulfur in it, and that produces sulfur oxides, which lead to sulfuric and sulfurous acid. So a normally working nuclear power plant should produce nothing but heat and some water vapor coming out of it. So that's a pro, certainly a pro for a nuclear power plant. Now, again, you've got to deal with that waste issue, which is certainly a big con to it. Let's look at 25. I think we've answered this question. What is a physical characteristic of spent fuel rods? I think that question means what's a physical characteristic of spent fuel rods? Sort of, as soon as they're spent in the short term, what's one physical characteristic of them that we've mentioned? Somebit?
It's mostly uranium-235.
Yeah, you're getting into, and whoever was writing that, we're going after the physical characteristic that they're still hot. Yeah, and it's you're true that there's still a good bit of uranium-235, though less than we had before.
Wait, did they start from uranium-238?
No, sir. They do contain uranium-238, but it's not helpful to the fission reaction per se. It's uranium-235 that's undergoing the fission.
Okay.
But part of this question is getting back to not a chemical property, not a nuclear property, but a physical property is just that they're hot, and they tend to be stored underwater. What happens to a fuel rod when it's no longer useful? Right now, what happens in the U.S. to nuclear, Willie?
All right, I actually had a question.
All right, go.
Like, why would you enrich like U-238? Like, why would you enrich it to where you have like a compound that's like mostly U-238? Why not like if you had the uranium-235 isolated, why not like pair it with carbon or something that was like a moderator naturally? And because it seems like you're just wasting a lot of like normal uranium.
Willie, I'm not fully clear on your question, so let's just make sure. So uranium in the ground is only about 0.001% 7% uranium-235, and you slowly enrich it so that there's more of it, and by the end there's, let's say, 3%, and that's what's in the fuel rod. Help me with your question a little more. I get the part about pairing carbon with it, but
like, is there not, like, when we enrich it, can you not do a process in which, like, you're isolating the U-235? Because I mean, it kind of.
No, sorry. Yeah, you do. Sorry, I get your question now. Okay. To isolate the uranium-235 and get it pure, that's sort of what you're asking. Then you've gone way past 3%, you're up to 100%. So essentially what we can do is, the easy thing to do, I should say, is to concentrate it to 3%. And easy is a relative term because it still takes very, very high technology to just do that. So if you buy that part, what a nuclear power plant wants to get from a supplier is uranium-235 that's only enriched to 3%. That means there's still 97% uranium-238 that's not necessarily useful to you, but you don't go to the cost of getting rid of that 97% that's just not in your way. Is that more clear as an answer?
Yeah, I believe so, yeah. Got it.
So then your 3% does the good stuff for you, and you don't want to enrich to 100% because then you've got the potential of your plant acting like a bomb. So you only go to the cost of enriching to 3% because that's useful and not ultimately very dangerous in terms of exploding.
Okay. That makes a lot of sense to me now.
Yeah, so you've asked a really good question. So you enrich the uranium to uranium-235 only 3%. That alone is expensive, but nowhere near as expensive as enriching it to a much higher degree. Excellent question. I love you guys. The questions you asked are just really good. And keep it up. Samvith?
In an ideal situation, how long would a pure uranium fuel rod last? U-235.
Pure.
Yeah.
Let's see. I don't think it would last long at all, and this is not meant to be funny, but I think as soon as you tried to react it, you'd have what's called a critical mass, and you'd have a bomb in your hand. So as soon as you tried to get a little bit of fission going, you couldn't stop it, and it would blow up. So pure uranium-235 would be highly, highly, highly dangerous, and just a little bit, starting it with a single neutron somewhere would be bomb worthy. So, you need to stick with a low 3%. Then you've got something that some of your neutrons are going to miss and not hit anything, and some are going to hit other uranium-235s, and you've got the ability to control it if it's only 3%. You can slow it down. You can not let it get too crazy and out of control.
So even when it's properly filtered, pure uranium-235 is still volatile.
I don't want to use the word volatile because I think of that in a different way, but it's highly explosive because, it's like a bomb ready to go off, no pun intended, because all it takes is a neutron to set it off, and that neutron then releases more neutrons, and then, you get a chain reaction that's Hiroshima. I mean, so yeah, it's extremely, extremely dangerous. What's the answer to what happens to a fuel rod when it's no longer useful? Well, we haven't found a good answer to that. Currently, they're stored on site. Ultimately, probably they'll be buried underground. But that right now is a question that our Congress has not agreed to decide. And they keep pushing it down the line and not deciding. So ultimately, right now, it just sits on site waiting for a decision to be made. Anybody? 27 says in the U.S. a new nuclear power plant has not come online since what date? The answer used to be 1970. So for the longest time, we didn't have a new nuclear power plant in this country until 1970. That has changed. I feel like one maybe came online in like 1996 now, so it's not that long. But we've only had a few since way before you guys were born. And I don't trust that 96 date. It's something I saw, and then only a few. The point there, the reason I asked that question is we went through a time in this country where we were pretty pro-nuclear. We built 100 nuclear power plants, but then in 1970, we pretty much stopped. We had an accident called 3 Mile Island. There was a little bit of radioactivity released from that, but it was a very scary thing. And then Chernobyl happened, and then more recently Fukushima happened. So there's concern about nuclear power and how to deal with it. And I think recently there's been sort of a revival of interest in nuclear power. Okay, Max found it online. It is 1996. But again, if you'd have to go back, wow, that's 45 years, 1970, right? 30. Yeah, we're 45. In the last 45 years, we've only had like one nuclear power plant come online.
Before that was 77.
All right, so I lied, 77. So okay, so that would still be like 38, almost 40 years. So we haven't added a whole lot to our nuclear processes, and I'm not proposing we do. I'm just trying to put out facts. But also the technology's changed a good bit since then.
Yeah, how is it possible that in the last 40 years, with just all the technological advancements that I would assume if there's not a new one, they're still running basically the same?
Yeah, they're running some of the old stuff. And I don't know whether maybe what they do is update their facilities. So that's a really good question. I think the last thing we have time to do is really 28. What's the most likely, not necessarily the best long-term solution for handling spent nuclear fuel is probably what they tried in Germany and would probably try here is probably deep underground burial. I've heard people suggest, hey, why don't we just blast it out into space? Costs about $1,000 a pound to lift anything off this Earth. And then you've got the whole question of, well, are we just going to put, dangerous stuff up into space? And what happens if we try to send it up and the spacecraft blows up? So I think we're stuck with it on this Earth. You guys have been asking such good questions. I want to make sure there's a chance for more questions before we wrap up. We got a couple minutes left.
I have a comment.
Chandler, please.
Yeah. Power plants. There's one that's supposed to come online possibly by the end of this year in Tennessee.
Oh, so, neat. Okay, thank you. You guys feel like you understand what a moderator does? Moderates the speed of the neutron. Do you feel like you know what a control rod does? Helps control the nuclear reactor from going too crazy by absorbing neutrons. You know what the coolant does? Okay. Do you know some safety features that a nuclear power plant has? Got the big containment dome that's made out of really big, thick concrete and steel. There, should be ways to shut the reactor down fairly quickly with control rods. Willie's got a question.
I think that I think it was in Fukushima. Maybe when it went critical, I think one of the designs is the whole rod just goes into a big body of water, or like a larger body of water. I can't. All right, never mind. I can't remember what it was. I'll get into it.
One of the problems at Fukushima they didn't account for was I think they always assumed they'd be able to have water coming in to help cool it, and the tsunami that they got there just knocked out. I don't remember if it was their electricity or something that was pumping the water in, and or somehow I need to go back and figure out more about that. But they didn't account for the amount of damage that tsunami caused, and yeah, I mean, looking at footage of that is an amazing, scary explosion where a large amount of radioactive material was shot up into the air. Okay, we're kind of out of time. We'll pick back up with this on Thursday. You guys, between now and Thursday, have a test for me. Good luck with that. Study up. Email any questions. And good job with the questions in class today. Take care. Oh, say hi to Olivia if it's not too late. Hi, Olivia. She's going to watch our video hopefully later. I should have done that earlier. Apologies, Olivia. All right, let's sign out of here.
Thank you very much, Mr. Walker.
See you, Robin. Bye-bye.
Bye.
See you, Sambit.
Have a good day, sir.
Thank you. Bye, Fort Worth Country Day.